Now we are ready to understand the Maxwell's equations. So let's start with the first Maxwell's equation, which is also known as the Gauss's law. When written in the integral form, the first Maxwell's equation looks like this, which states that for a closed surface S, the surface integral of this electric field E is equal to the amount of charge Q that is inside this closed surface divided by permittivity of free space. We have a name for this surface integral. We call it the electric flux. Now, when we evaluate the surface integral, we have to evaluate the electric field at each point on this surface S. Okay, so one of the implications of the first law of Maxwell is that if an electric field like this one originates from some point P, then there must be a charge on that point P. Let's see a very easy proof of this thing using first law of Maxwell. For that, let us imagine a closed surface around this point P. Now, as electric field is only going outside from here, but no electric field is entering here, so the net flux phi E here is non-zero. But according to Maxwell's equation, you can see if the flux is non-zero, then the quantity on the right hand side should be non-zero too. So that means the charge Q inside is non-zero. So there must be a charge here inside this closed surface. Now, if you make this closed surface very small, then you will see that the electric field line must originate from this point P. So, Maxwell's first law implies that electric fields originate on positive charges and terminate on negative charges. And everywhere else, the field lines can twist and turn in space, but they cannot start or stop anywhere else. Now let's concentrate on the second equation of Maxwell. This is the mathematical expression of the second equation, which says that for a closed surface S, the surface integral of the magnetic field is actually equal to 0. Now, why is this thing 0? We know that magnetic fields generate from the North Pole and it ends in the South Pole. And as we do not have any magnetic monopoles available in nature, the field lines which originate from the North Pole will end in the South Pole, and so in a closed surface like this, we'll have net magnetic flux equal to 0. Now let's turn to Maxwell's third equation. For that, let us consider an experimental setup like this. Say we have a loop of wire like this and a magnet like this. Now we are moving this magnet in and out through this loop with some velocity. This movement of the magnet will create an induced current in this loop. Now, this induced current implies that there is an electric field or equivalent electromotive force present here. The relationship between this electromotive force and electric field is given by this equation. Well, this is not surprising, as electromotive force can be considered as some kind of potential, and we can write each potential as some line integral of the electric field. So this induced electromotive force in this loop of wire is equal to the line integral of electric field over this loop. Now, Maxwell's third equation is actually a rewrite of Faraday's law. Now, according to Faraday's law, the electromotive force induced in this loop is equal to the rate of change of the magnetic flux in the loop with a negative sign. Now, we can write this electromotive force as the line integral here and the magnetic flux in the loop as a surface integral of magnetic field through this loop. So we have seen that a varying magnetic field induces a current in a loop. But can a constant magnetic field induce current in a loop? Well, it can if we mechanically rotate a coil in a constant magnetic field, because this action of rotation changes the magnetic flux inside the loop. Now, in this case, we see that there is no induced electric field. So how can we have the electromotive force like this? In this case, we can redefine the electromotive force to be like this, where we replace the electric field with this term, which is the magnetic force per unit charge. Now, we know that a moving charge feels a force when it is in a magnetic field, and the amount of force is Q times V cross V. So we can write down the electromotive force to be equal to this quantity. So in case of a rotating loop, we have to replace the electromotive force with this quantity in the third equation of Maxwell.